So the last time I think we looked at Maverick brilliantly presented on effect size and effect modification. I'll briefly highlight some practical examples of this. So the outline for my presentation today is I'll give a general recap of what we have been seeing for the past weeks. And I'll introduce something which is a bit different, but I feel like we will not do it justice if we don't mention it when we are talking about causality and bias. So I'll bring in the aspect of propensity scores, which is also another way to adjust for confounding. And then I'll give some case examples, particularly focusing on effect modification. So my goal is to, at least with some practical examples, help consolidate the comprehension of effect modification. But before jumping into maybe the meat of what we have to do today, maybe a bit of recap. Normally, in epidemiology, we know the gold standard is clinical trials because we can really control for confounders, but not everything. We don't have the resources, and sometimes it is even unethical to get to perform a clinical trial. So what we do is we use observational studies. But from these observational studies, if they are properly conducted, then we can get coarser uh, some coarser conclusions or coarser inference from them. But there is always an elephant in the room, which is this third variable. And it is always important to label the third variables because depending on the role that each of the depending on the role of the third variable, you will either have to control it, you will not have to control it. So this is particularly important. And as Merve clearly said, like we say something, let's say we have an exposure A and we have there's a typo here, but don't bother. On the right, it should be the outcome Y. We say that this other variable, which is called V, is a modifier of the effect of A on Y when the average of this effect varies across the different levels of V. You can just assume like, yeah, there's a bit of fire and at different intensity of the fire, you have different effect sizes. And to maybe bring this back, I think we saw this when we looked at confounding. Normally, when you start with confounder, when you have a third variable in mind, to make things simple for the each of exposition, considering it is a categorical variable, what you want to do is you start with your exposure and outcome and you get the crude analysis. Crude analysis means without considering any adjustments for any particular variable, you get the effect size, be it odds ratio, relative risk, hazard ratio. And once you get this, now if we consider we have a third variable which is called a third variable which is categorical, then we can get a scatum specific estimate. And now we compare, are these scatum specific estimates the same? If they are not the same, then yeah, we are looking at the aspect of confounding, and then of course there are some further uh, things downstream to really confirm if that thing is a confounder or not. But now, if these cartoon specific estimates are very different, then you might be having a scenario of effect modification, and in that sense, you want to report not the crude analysis, but you will report the cartoon specific estimate. So, but before jumping into like maybe practical examples of of effect modification, there's one thing in like modeling or maybe statistics in general, like you can adjust for confounding during the implementation or phase of your study, that is the planning phase, during data collection by doing matching of individuals and or restricting individuals to a particular group. If maybe a third variable is like age, you might restrict it to maybe a particular age group, and therefore you eliminate the confounding effect. But the good thing about confounding is that when you move towards the aspect of analysis, you can still you can still handle that, contrary to maybe like selection bias and information bias, which are not pliable to analysis or adjustment during analysis. So Practically, what the propensity score does is that it kind of like models the probability of somebody being exposed to a particular risk factor, or if it's in an interventional study, the probability of somebody being in the treatment group. And the theory about this is that normally as I mentioned on the mice clinical trials, the focus is that you want to ensure that the two groups or the two arms are very similar, such that at the end of the day, the effect you will be getting will be just that will be completely attributed to the treatment and not to maybe any noise or differences in the groups. This is not the case when you do observational studies. So what propensity scores is doing is kind of like it's trying to balance up the groups. And yeah, the first thing is that in this stage is that you get these propensity scores, which are these probabilities, and downstream you can do a whole tons of different statistical methods and analysis. You will see things like inverse probability, treatment weighting, propensity score matching, which is kind of analogous to matching when you are doing the implementation phase of your study. And also you have the stratification of propensity scores, which is kind of like the stratified analysis you do when you're looking for effect modification. So this is something which is particularly important. I will give so as I mentioned, this is just like the first stage. It's a two-stage process when you want to use this propensity score. First thing is that you want to model the probability of being in the treatment group or the exposed group if it's in the context of an observational study. So what you do is that you have to clearly state your confounders, and clearly stating confounders means you really want to maybe go through literature, talk with experts in the domain, and then you come up with a clear directed acyclic graph which really maps out all of the rows of all of the variables, so you really know which ones you want to control for. Once you get these confounders, you calculate your probability or the propensity score, which is that probability. And then now you'll be getting the weight. So the notion of the inverse probability weighting comes from, like, you take the probability you calculate for somebody to be in a particular group. So that is the treatment group or the exposed group. You take the inverse of that, and that is the weight. And then what this does is like it creates some form of a pseudo population where like the exposure status now becomes independent to the confounders. And in statistics, when they say something is independent to confounders, it means there's no relationship between those two variables. And of course, if there's no relationship between those two variables, then you break the cycle of, or I don't know, the relationship of confounders, and then you can be sure that what you get from an observational study is closer to the causal effect. So here is not a hypothetical example, but a real scenario in a nephrology clinic where you have an exposure which is extended hemodialysis and conventional hemodialysis. So extended hemodialysis here is hemodialysis beyond 6 hours. But now the challenge is that people with extended hemodialysis, they were younger, they suffered less from cardiovascular comorbidities and diabetes, and they were more likely to have received kidney transplantation. And you see that all of these factors, like these are just these are signs of good prognosis. So you want to expect that mortality, which is the outcome here, will not be really severe in this group. So what we do is that as you can see in the original sample up here, we are balancing now the diabetes distribution. We see that in the original sample, the conventional hemodialysis group, you have three diabetic people and one person who is not diabetic. But now for the extended hemodialysis group, which is maybe the interventional group, if we want to say so, you have just one diabetic. What this propensity score does, is that it creates this pseudo population. You see that now, instead of 75% and 25% that you get from the original sample, it kind of weighs everything up. And if you count now, because if you count all of these 1.3 plus 1.3 plus 1.3, that makes like 4 diabetic people out of the 8 here. And the same idea here. So you kind of balance it up. So you eliminate the aspect of diabetes being a potential confounder. And then, of course, the effect will be seen will be something which is closer to the glucose effect. So that being said, I will now move forward onto the aspect of effect modification. As I mentioned, effect modification simply means that at different levels of a particular variable, you have different average effects. So I have this I am starting with this hypothetical example, then I'll give a real life scenario. So let's just say we have exposure, which is age, and then we have disease progression, and we assume there's a linear relationship between them. So normally, if I don't consider treatment, I see that, of course, there's a clear linear relationship between these two. But now when I go further into the analysis, I look at like I fit different linear regression lines to them. You clearly see that these two lines are not parallel. When these two lines are not parallel for linear regression, which is the coefficient you get or the slope of the line, this simply means that the effect of this of H on the disease progression is different in the two treatment groups. And if you fit your model when you see this kind of effect and you don't adjust for this, it means you are forcing your linear regression models to have the same slope in each group, which is kind of like the wrong thing to do. So the step to take further is you start with your base model, which has just like we call it like the main effects. So the main effects of treatment and the main effects of age. We see that of course increasing age leads to like a unit increase in age, you have that amount like 0.3 increase in the mean outcome of disease progression. But now when we start taking into consideration that the slopes, of course, are very different, then you see here on the left, you see that this interaction effect now there's a significant interaction effect as it was depicted by the different slopes that we saw there. So now the correct model to look at or to interpret is not this model on the left, but the model on the right that includes the interaction effect. And for you to interpret this model, it is only valid if the main effects of the different variables are there. So you can only interpret all of these coefficients if you have your treatment and the age in the model. Otherwise, you will be having something, otherwise you have something very different if you are not very careful. So I will take maybe a similar case, similar scenario, age, and then the disease progression. Then, but you will see now that the lines are pretty parallel. So you see that the slopes of these two lines are the same. So I am I am hypothesizing that there is no interaction effect between these two. So what I do further is that I I feed the model without the interaction term, and I feed the model with the interaction term, and you see that this is not significant. You see that the coefficient here, the null value for the coefficients of linear regression is 0. So because this confidence interval includes 0, it means this is not necessary in the model. And of course, in statistics, there's something called parsimony. So you want to ensure that you don't have a very complex model unless it is required, because adding an interaction to interpret your model becomes pretty challenging. It's not as easy as maybe when you have just these two additive variables. So the right model to fit will be the one on the left. You drop the interaction term and you focus on the one on the left. Then now I'll move to this case of a practical case of the duolar heart failure registry, which is we looked at the effect of baseline heart rate in patients with heart failure, and we looked at the survival after 12 months, and we wanted to see what actually was happening. So when we did some analysis, this is the crude effect we had. So we kind of like to ensure that the effect size made some sense. We got the hazard ratio for every 10 unit increase in the heart rate. And we can clearly see that for every 10 unit increase in the heart rate at a given point in time, is a 19% chance of there's a 19% increase in mortality. And this is of course significant because we see the 95% confidence interval does not include the null value here, which is 1. But now an interesting thing we found was that when we stratified or when we looked at this effect on hypertensive and non-hypertensive people, we saw that it was more on people who had hypertension. So people who had hypertension at every given point in time, the hazard ratio was like so they had the 30% chance in mortality. But for those without hypertension, 9% chance of increase in mortality. But of course, the null value here includes one. We don't have to focus more on the p values because of course when you stratify things, the sample size decreases, and maybe if had it been the sample size was a bit bigger here, you will see something which could have been significant. So we don't focus too much on the p value. But the key thing I want to highlight here is that when you have something like this, then of course you want to present the results not as the crude effect of hazard ratio for the 10-unit increase in the overall population. You have to consider that for different subgroups of the population, then this effect of heart rate changes. So this is the publication we had. I think if you want to get further information, you can look into it. And now there is also another thing. In statistics, do you adjust for every variable or should you not adjust for every variable? It becomes it's really challenging because you just have to think of these state variables as like they either open a backdoor to the like they open a backdoor connecting the exposure and the outcome, or they close the back door. So if the back door is closed, that is good. If the back door is open, that is not good because it leads to a spurious correlation. So I have this generic example here. So I have my A variable and it causes both X and Y, but X and Y causes Z. So we know that the confounder, this is a clear definition of a confounder. A here is a confounder. A causes the exposure, and A causes the outcome, but A is not in the causal part, which is a clear definition of a confounder. And here we even see that there's no causal relationship between X and Y. And now for the collider means, or a variable is called a collider when it is caused by both both your exposure and the outcome. You can see that the arrows are leading to this. For one, you have to control for or adjust for the other one, you don't have to control. So here, if you are controlling for the confounder, you close the back door, which is good. Here, if you don't here without if you control for the collider here, you open the back door, so you don't want to control for it. So we see that of course this way created like simulated these variables to ensure that they have a linear relationship. So you have Y and A, of course they are both simulated in the same way, so they have a clear linear relationship. And now if I look at the relationship between Y and X, there is no relationship or causal link or link between these two. But just because they share something, the confounder, you see that there's a strong linear relationship, which if we are not very careful, this might lead to maybe some causal conclusions like, oh, X causes Y, but that is a spurious correlation. There's something which is very pertinent in statistics, like correlation is not equal to causation, that is a key thing to carry alongside when you are doing any analysis. And now I looked at different candidate models to see what is actually happening. So the first scenario, I modeled Y on X, so where there is no relationship, but we see that because I did not adjust for the confounder, which should have closed the back door, what happens is that I see that there is a relationship. So the different, like the 1 unit increase in X is almost equivalent to a unit increase in Y. Of course, that is a spurious correlation. But now when I close the back door, you see the coefficient of X now becomes negative, and it is not significant because the 95% confidence interval you would include 0, which means it's not significant. And therefore you have to control for the confounder here. But now, if I take my variable here, so I am modeling X on Y, so I'm looking for the average of Y using X, and then my third variable, which is Z, which is the collider. The collider, if I add the collider to the model, it opens the back door, and you see that now I have this significant relationship. And one thing you will notice is that the coefficients are very different, which is very important to take note of. So normally, if something is a collider, you want to avoid it. You really want to avoid it when you are doing your analysis. And maybe highlight something also about confounders. Like if you draw your directed acyclic graphs and you have confounders, it becomes a bit complicated because you could adjust for some confounders, and that will warrant that you have to adjust for more confounders. So it's something that is very important to take into consideration when you want to perform your analysis. Then there's this aspect of, we have seen two nice examples of effect modification. There's also one thing of a third variable, which is called a mediator. So it means it has a relationship between exposure and outcome, but now it is in the intermediate pathway. And because of this, now you have two pathways to get to your outcome. You have the indirect pathway and you have the direct. So the direct pathway is just this direct link between the exposure and the outcome. And then now the indirect pathway is this other route that it takes from E to M and then back to O. And normally in regular regression models, if you are adjusting for your if you are adjusting for your mediator variable, what you are doing is that you are kind of blocking the indirect part. It means what you get from your model is like you are looking at only the direct pathway. And Peter has more experience in mediation analysis in the sense that you could have a scenario where there is complete, like in there, the indirect pathway completely explains everything and the direct pathway explains nothing. So if you block that and you find yourself in a scenario where the direct pathway explains nothing and it is completely explained by the indirect pathway, then you, of course, find yourself in trouble and you get results that are not accurate. So it's something very important to keep in mind. So I have a practical example here, still from the Douala heart failure registry. I did not go more into the mediation analysis because it becomes a bit complicated when you're going to do survival analysis. But here, the notion is that you have age, and as somebody ages, the glomerular filtration rate drops, and of course, the dropping of the glomerular filtration rate, when it reaches a threshold, you say that person has a chronic kidney disease. So yeah, and chronic kidney disease is a huge risk factor for mortality. But you see that chronic kidney disease is in the pathway, is always in the course, is in the causal pathway. Something is an intermediate step before mortality. So if normally you want to maybe fit a regression model here, if I'm looking at the Cox regression model and I adjust for CKD while I have H, then it means what I will be getting, it will be just like the direct effect, the direct pathway between H and mortality. And mind you, if in reality this effect is completely explained by this indirect pathway, then of course what you get will be completely wrong. So it's something which is very important. I think the presentation was not very long. Yeah, I think, yeah, these are some good references to get more into these things. And